found by measuring the temperature change when the acid reacts with an alkali. So this is an acid-base titration. And what we are trying to do is we're trying to find the concentration of an acid. It's an exothermic reaction, so we have a negative delta H. And so the temperature change is there's going to be an increase in the temperature. You will determine the concentration of sulfuric acid by adding aqueous sodium hydroxide of a known concentration to sulfuric acid and measuring the temperature change. It says here Fa1 is our sodium hydroxide of this concentration and Fa2 is our sulfuric acid, and we are trying to find the concentration of this. So here the method says to support the cup in the 250 centimeter cubed beaker. So we have a 250 centimeter cubed beaker and we have a polystyrene, most likely, cup inside. It says pipette 25 centimeters cubed of the sodium hydroxide into the cup. So there is 25 centimeters cubed of 2.01 moles per decimeters cubed of NaOH. Then it says place the thermometer into the sodium hydroxide in the cup, tilt if necessary to ensure the bulb of the thermometer is fully covered, and record the temperature of sodium hydroxide. This is the temperature when the volume of sulfuric acid is 0 centimeters cubed. So essentially we're going to have a thermometer in here. This is going to measure the temperature of our sodium hydroxide solution, and our initial temperature that it will be recorded is when there is 0 centimeters cubed of sulfuric acid, because we haven't added any yet. Then it asks for us to fill the burette with sulfuric acid. So there's going to be a burette, and it's going to have sulfuric acid. Let's just pretend it's filled so I don't have to shade. This has H2SO4. And then it asks to run 5 centimeters cubed of sulfuric acid into the cup. So we're going to add 5 centimeters cubed. So the scale right here on the side must decrease by 5 centimeters cubed. Then it asks us to stir the mixture and record the maximum temperature into table 1.1. So at the start, when we recorded our temperature, it filled this in for the temperature. Then after we run 5 centimeters cubed, we record the maximum temperature once again. Then it asks us to run further 5 centimeter cube proportions of sulfuric acid into the same cup. So what we do is we just keep running 5 centimeters cubed and recording the temperature after each one. From that we can record our temperature change. It says after each addition, stir the contents of the cup and record the maximum temperature for each addition. So I've provided us with some estimates for temperature readings at the different additions, and there are just 2 things we need to note. The first thing we need to know is that all our answers should be to 3 significant figures. That is because the question asks us to use appropriate significant figures in our answers. The second thing we need to know is that all our temperature values must end in 0.0 or 0.5. Now this is because school lab thermometers measure either to 1 degree Celsius or every 0.5 degrees Celsius, and if we were to note down an estimate like 0.2 or 0.4, that wouldn't be justified because we are simply guessing beyond the instrument's resolution. Now this was a 4-mark question, so let's take a look at what the 4 marks are for. So the first mark is for giving all 9 readings. The second mark is for ending our readings in 0.0 or 0.5. The third mark is for our maximum temperature, so in this case 34 degrees Celsius, to be within 2.0 degrees Celsius of the supervisor at your school's maximum temperature. the fourth mark would be given if your reading is actually within 1.0 degrees Celsius of the supervisor's maximum temperature. So part B asks us to plot a graph of temperature on the y-axis against total volume of sulfuric acid on the x-axis. They want us to select a scale for the y-axis to include a value 3 degrees Celsius above our maximum temperature reading and label any points you consider to be anomalous. Draw two lines of best fit. The first line for the increase in temperature and the second line after the maximum temperature was reached. Extrapolate the lines so that they intersect, and the intersection corresponds to the volume of sulfuric acid needed to neutralize the sodium hydroxide in your experiment in A. So the first thing I'm going to do is I'm going to start by labeling my axes. So first of all, the x-axis is the volume of sulfuric acid added. Then on my y-axis, this is the temperature of the solution. Then I must add units to my labeled axes. So the volume is in centimeters cubed. The temperature is in degrees Celsius. Once I've done that, I need to generate scales for each of my axes. So if we look at the x-axis scale, there is an increase in increment of 5. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9 big squares. So I can just start with 0.00 and end with 40.00 and go up in increments of 5. So 0.00, 5.00, 10.00, 15.00, 20.00, 25.00, 30.00, 35.00, 40.00. If we look at our temperature, we may want to make sure we can include up to 37 degrees Celsius because it did ask us to ensure that we can include a value of 3 degrees Celsius above our maximum temperature, and we must include our smallest temperature of 21 degrees Celsius. Now this may take you some time to figure out, but always think of the basic scales you can use. So you can go up in 1s, in 2s, in 5s, in 10s. These are the most common ones, but you have to make sure that your scale isn't too big because you want to fill in at least half of the graph. So I've chosen to go up in increments of 2, and I'm going to start with my minimum temperature. So this is going to be 21.0, this is going to be 23.0, 25.0, 27.0, 29.0, 31.0, 33.0, 35.0, and 37.0. Okay? Next, what we need to do is we actually need to plot our graph accurately. So now that I've plotted all the points as accurate as possible, so it says here we need to extrapolate 2 lines of best fit. The first line is for the increase in temperature, and the second line is after the maximum temperature is reached. Our maximum temperature was at 25 degrees Celsius, which is right here. 34 degrees Celsius at 25 centimeters cubed. So our first line is going to be all of this till 34 degrees Celsius, and our second line is all of this after 34 degrees Celsius. Now this first section seems like a curve, so I'm going to draw a curve of best fit, and I'm going to extrapolate beyond 34 degrees Celsius. And then our second line seems like a line of best fit, so I'm just going to draw a straight line through. As you can see, they both intersect at 25 centimeters cubed, because if we draw a line downwards from the point that they intersect, we meet at 25 centimeters cubed. Therefore, 25.0 centimeters cubed of sodium hydroxide requires 25.0 centimeters cubed of sulfuric acid. Now this question was worth 5 marks, so let's take a look at what each mark is for. So for the first mark, we needed to label our axes and provide their units and use a suitable scale. The scales that would have been accepted here are increments of 1, 2, or 5 per 20 small squares. Let me just move that up. Then our second marking point is for accuracy in plotting, and that is ensuring your points are in the correct places. Marking point 3 was for your best fit lines. And that would mean one curve, one line or curve for the second line of best fit. The fourth marking point is for extrapolating the lines to intersect at or above the highest temperature. And the fifth marking point was for finding the correct volume to 1 decimal place. And that is because we've used our volume of sodium hydroxide to 1 decimal place. So it's only right to use our volume for our sulfuric acid to 1 decimal place as well. So part C asks us to calculate the number of moles of sodium hydroxide pipetted into the cup. Now remember, the volume we used was 25 centimeters cubed and the concentration we used was 2.01 moles per decimeter cubed. Now the number of moles is equal to the concentration times the volume. So the number of moles is equal to 2.01 times 25 divided 1,000. We must divide by 1,000 to convert into decimeters cubed, so that the 2 decimeter cubed units cancel out and we're left with moles. Now 2.01 times 0.025 equals 5.025 times 10 to the power negative 2. So that is our answer for the number of moles of sodium hydroxide. The next part of part C asks us to calculate the concentration of sulfuric acid, and it's given us the equation. So the molar ratio of sodium hydroxide to sulfuric acid is 2 to 1. That means the moles of sulfuric acid are going to be half of the moles of sodium hydroxide. So we're going to take our moles of sodium hydroxide and we're going to divide them by 2. And we get 2.51, let's round up, 3 times 10 to the negative 2 moles, and it wants it per decimeters cubed. So our concentration equals our moles divided our volume, and we found our volume to be 25 centimeters cubed. So our concentration equals 2.513 times 10 to the power negative 2 divide our 25 divided 1,000, which is 0.025. 2.513 divide 0.025. we get 1.0052. However, I think it would be more reasonable to give our answer to 4 significant figures, so we will end up with 1.005. Question number 2. Acids react with carbonates to reduce carbon dioxide gas. This is the equation for the reaction that occurs when sodium carbonate reacts with sulfuric acid. The reaction can be used to determine the concentration of acid by using the mass of carbon dioxide released. So usually when we're doing reaction rates and gases are produced, we will use a gas syringe to measure the amount of CO2 produced via the volume of gas in the syringe. However, this time we're using mass released. What will happen is as CO2 gas is produced, it's going to escape because it is a gas and result in a reduction in the mass of the reaction mixture. So you will determine the concentration of sulfuric acid in Fa2, the same one that was used in question 1. And we have a new reactant called Fa3, and that is basically just our sodium carbonate solid. So if we take a look at what we're actually doing, let's take a look at our method. Use 25 centimeters cubed of a measuring cylinder to transfer sulfuric acid into a conical flask. Then weigh the flask with the acid and record our mass. So we have a conical flask with 25 centimeters cubed of H2SO4. We weigh its mass, and then so let's say we weigh our mass, usually to 2 decimal places. And then we take a container containing the sodium carbonate and we record its mass. So usually we'd use a weighing boat. And this would be our sodium carbonate. And we're going to use 6 grams for this experiment since they haven't specified the mass. Then they want us to carefully tip all of our sodium carbonate into the acid in the conical flask. Swirl the contents occasionally and do so until the fizzing stops. So then we're going to add our sodium carbonate to our flask, and some fizzing is going to take place because CO2 is being produced. Now in this experiment we're using mass of carbon dioxide released rather than the volume like we would using a measuring cylinder. And so as you can imagine, since CO2 is going to be produced, we're going to have a decrease in the mass of the contents in the reaction mixture. It wants us to weigh the container with any residual Fa3 and record the mass. This is because when we transfer our sodium carbonate into the flask, not all of it will be transferred and some may actually remain. Some little bits of residue will remain. Now, you may argue that you might want to add washings to our solution, but then we're actually going to be diluting the solution and we won't find the actual concentration, so we do not add washings to the flask. It then wants us to record the mass of Fa3 added, the mass of sodium carbonate added. So the mass of sodium carbonate added is the mass of sodium carbonate minus the mass of the residue left behind. Then it wants us to calculate and record the total mass of the flask, the acid, and the sodium carbonate. So the mass of this. And then they want us to reweigh once the fizzing has stopped. Then it wants us to record the mass and calculate and record the mass of CO2 given off during the experiment. So this is going to be, we're going to want to record the mass before and after. And the amount of CO2 produced is equivalent to our before minus our after, because any loss of mass is due to the production of CO2. Now it's asking us for the results, and that is the masses that we have recorded. So throughout the method, highlight wherever it says record the mass. So it says it once here, 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 and here. So that is 1, 2, 3, 4, 5, 6, 7. So my table must include 7 masses. Okay, so the masses we're going to have 7 subheadings. And I'm going to write out what they are before I actually draw my table, just so it's a lot neater. So the first mass we recorded was the flask plus the acid, so plus Fa2. Then, that's that right here. Then we recorded the container plus Fa3. Then down here we calculated the residue of Fa3. Then right here we calculated the mass of Fa3 added. Down here we calculated the mass of the flask plus the acid plus Fa3. Right here we recorded the mass of when the fizzing had stopped, so the mass of the flask and contents. So flask and contents after the reaction had taken place. And then last but not least, right here, we recorded the mass of carbon dioxide given off, or the mass lost. So I'm going to say the mass of the carbon dioxide. Now I haven't specified that these are masses, so I'm going to make a bigger heading up here and write mass in grams. Now I can draw my table. Okay. To the right is going to be my actual values, and to the left just indicates what those values are for. So I have come up with estimates that will give us the correct answers and align with the theory of all of the questions that come up with this experiment. And I have taken the weighing boat to weigh 0.23 grams, and I have used a starting mass of 6 grams of sodium carbonate, which would be provided to you by the school. It is important to note that 2 of our values are calculated, so this value is a result of a subtraction of these 2 values. This value is from the subtraction of these 2 values. And all my values are to 2 decimal places as shown on a balance. If your mass balance records to 3 decimal places, then you'd use that instead. My table is in grams, so I've stated the units, I've included all the headings, and so that should earn me the 5 marks. It then asks us to calculate the number of moles of carbon dioxide given off in the reaction. This is the formula for carbon dioxide, and we need to remind ourselves that the number of moles denoted by N is equal to the mass in grams over the molar mass of the substance. So the MR of CO2 is equal to the MR of the individual atoms. So one carbon atom has an MR of 12, and oxygen atoms have an MR of 16. We'll end up with an MR of 44. So our number of moles is going to be the 2 grams that we had produced, divide 44, and that will give us 0.0455 moles. The mark scheme wants the answer to this question to be from 2 to 4 significant figures. It then tells us that the sodium carbonate added was in excess and that we need to show by calculation that this is the case, using our answer to Bi. So in Bi we calculated the number of moles of CO2, and if we look at our equation, you can see that the molar ratio of sodium carbonate to CO2 is 1:1. So if we calculate the number of moles of sodium carbonate, then perhaps we can do something with that. The number of moles of sodium carbonate again is going to be the mass divided the MR. The MR of sodium carbonate is going to be 106, obviously just by using the individual MRs. So they are as follows. So the number of moles is going to be the mass that we had added, and we added 5.91 grams. Divide that by 106, and we will get approximately 0.0558 moles. Now the number of moles of CO2 produced is 0.0455, and since 0.0558 is greater than 0.0455, we can say that sodium carbonate is in excess. Now, since our sodium carbonate is in excess, our moles of sulfuric acid is actually going to be equivalent to our moles of CO2. Therefore, the moles of sulfuric acid are equal to 0.0455. Now, at the start, we used 25 centimeters cubed of sulfuric acid. So to calculate the concentration in moles per decimeter, we have to do 0.0455 moles divide 25 divide 1,000. We divide by 1,000 to convert centimeters into decimeters. This will give us a value of 1.82, again from 2 to 4 significant figures. Now this value is a lot greater than the value we obtained in the first experiment, so this does say something about accuracy. But let's move on to part C. So here it says a student didn't have a conical flask and used a beaker instead. Explain why a conical flask is better. Now, using my own wording, I'd say conical flask reduces spilling. And I can explain why as well. So conical flasks look like this and beakers tend to look like this. If you look at the necks of the two, you can see that beakers have a much wider diameter at the top. This means that while you're swirling, it is more likely to get spills from the reaction mixture, and thus you're more likely to lose some reaction mixture. So with a conical flask, you'd lose less reaction mixture. Here it says that two students made suggestions on how they would improve the experiment to determine the concentration of sulfuric acid. In each case, the teacher told them that their methods weren't suitable. They want us to explain in each case why the methods are not suitable, and they don't want us to base it off of quantities or reagents. Quantities of reagents. Student 1 suggested using magnesium instead of sodium carbonate. So if we look at the reaction between magnesium and sulfuric acid, we will end up with hydrogen gas. Hydrogen gas has an MR of approximately 2, while CO2 gas has an MR of 44. This means that hydrogen is actually very low density because it has a lower MR. Now what this means is there's going to be a higher percentage error for small measurements. And let me explain how. Well, to calculate percentage error, it is equal to the uncertainty over the measurement made times 100. So if, for example, let's just call uncertainty U. Our uncertainty for mass due to the mass balance is plus minus 0.01 grams. And we lost 2 grams of CO2. We would have lost 0.1 grams of hydrogen for the same number of moles. 0.01 times divide 2 times 100 gives 0.5% percentage error. But 0.01 over 0.1 times 100 gives 10% percentage error. Hydrogen gives a greater percentage error. Therefore, it isn't suitable. Student 2 suggests using calcium carbonate instead. So if we look at the reaction between calcium carbonate, the only difference is we have calcium sulfate produced instead of sodium sulfate. Calcium sulfate is a solid, it is insoluble, while sodium sulfate is soluble. Now the issue with this is because calcium sulfate is insoluble, it may actually coat our calcium carbonate. So this reactant right here, preventing further reaction. That is because if we're blocking the calcium carbonate, there is less to react with sulfuric acid, but not all of it has been used up. Therefore, it will give us an inaccurate mass loss measurement. Part D asks us to state the uncertainty in a single reading of our balance. If your balance reads to 2 decimal places, then it reads to the nearest 0.01 grams. If it reads to 3 decimal places, then it must read to the nearest 0.001 grams. So the percentage, the uncertainty in grams is going to be our values divided by 2. So mine reads to 2 decimal places, so my uncertainty is going to be 0.01 divided 2, which is equal to 0.05 for a single reading. Now it asks to calculate the maximum percentage error in the mass of the sodium carbonate that we weighed out at the start. Now if we go back to our table, the amount of sodium carbonate added was a calculated value using 2 of our masses subtracted by each other. Since the uncertainty for one single reading is 0.05 and we've taken 2 to calculate the mass of Fa3, our uncertainty is going to be 0.005 times 2 over the mass, sorry I should have looked, which is 5.91 grams times 100. Like I said earlier, the formula for the percentage error is equal to the uncertainty over the measurement made times 100. So when we calculate that, we will get a value of 0.169%. And this is a very low value as percentage errors tend to be. So for experiment or question number 3, they ask us to do a series of test tube reactions and to write down our observations. So for this, all I can really say is try and write down as much as you possibly can. For example, in question AI, they asked us to heat the tube gently and then more strongly. So give your observations for before and after. This is a 2 marker, but it required 4 points to be made. So just try to state as much as you can. However, what we can do is we can use the observations that we should have written down to figure out what our compounds are. I also suggest to look at mark schemes relating to paper 3, just so you know what colors are accepted and what aren't, and how specific you have to be. So for this question, we have to figure out Fa4, Fa5, and Fa6. They're all compounds of the same metal in different oxidation states. This is an indication that this is a transition metal. So we might have a few in mind already, but we can use the reactions to confirm our metal. So it's asking us to use observation to suggest the identity of the metal present in all three, and to identify the oxidation states in each of the three compounds. So for Fa4, the first test tube reaction that we carry out is we heat it gently in a hard glass test tube and then more strongly. Initially we get a purple solid and a black solid, then the solid pops and the gas relights a glowing splint. So what we can infer from this is, since the solid popped, we can sort of presume that gas evolution has taken place. And this gas relights a glowing splint, which means that oxygen has been produced. That must mean that the compound contains oxygen atoms. Initially, it is a purple solid and it is a transition metal involved in the compound. So I'm going to assume that these are actually purple crystals. And one you should be familiar with would be KMNO4, potassium manganate. Now the black solid is probably going to be our magnesium dioxide, and that has been formed from the thermal decomposition of potassium manganate. Then it says we've taken our Fa4, which is our potassium manganate, and added it to 5 centimeters of distilled water and 1 centimeter of dilute sulfuric acid. This means we have essentially acidified our potassium manganate. Now this is actually a very strong oxidizing agent, and it oxidizes other substances. So what we've done is we've carried out 2 tests with our acidified potassium manganate. We've carried out test 1 by adding it to aqueous iron 2 sulfate. Now what this will do is it's going to turn our Fe2 plus sulfate and oxidize our Fe2 plus iron ions to Fe3 plus iron ions. Now a solution containing Fe3 plus ions is going to be yellow. Now in test tube number 2, hydrogen peroxide is added to our acidified potassium manganate, and we get a purple solution originally, but it becomes colorless. Effervescence takes place, which relights a glowing splint. Must mean O2 was produced, and that's what caused the effervescence. O2 from hydrogen peroxide is actually oxidation by the acidified potassium manganate. When potassium manganate is reduced. When it oxidizes, it's reduced to Mn2 plus ions, which form a colorless solution, while manganate ions are what form that purple solution. So here, for Fa4, we added it to a hard glass test tube and we heated gently and then more strongly. So the observations we had was it was initially a purple solid, and we had a black solid form, and then when we heated more strongly, the solid popped and the gas produced relighted a glowing splint. So since a glowing splint was relighted, then we know that that's oxygen for sure. Since the solid pop, we can infer that there was gas evolution, and that gas was the oxygen. Purple solid could be purple crystals, and this means that it was most likely potassium permanganate, since we have manganate here and it is a transition metal. The black solid that we had initially is most likely manganese dioxide, and that is a black solid, and it's formed upon the thermal decomposition of potassium manganate. So then it says we dissolve a small spatula of the potassium permanganate into 5 centimeters of distilled water and then 1 centimeter of dilute sulfuric acid. So essentially what they've done is they've acidified our potassium permanganate, and that our acidified potassium permanganate is a very strong oxidizing agent. So it oxidizes other substances while it itself is reduced. So we carried out 2 tests with the acidified potassium permanganate. The first test is with aqueous iron 2 sulfate, and we expect Fe2 plus ions to be oxidized to Fe3 plus ions. And if we take a look at our observations, our purple solution, so originally our potassium permanganate solution becomes yellow, and it's yellow due to the presence of the Fe3 plus ions. In the second test, we added it to hydrogen peroxide. We got effervescence, which indicates a gas has been produced. This gas relights a glowing splint, which means oxygen has been produced. And this means that our hydrogen peroxide was oxidized to form oxygen. Our observations for this is our purple solution becomes colorless. That is because when our MnO4 minus ions are reduced to Mn2 plus ions, they result in the oxidation of the hydrogen peroxide, and our Mn2 plus ions form a colorless solution. So here they added the original potassium permanganate sample to 5 centimeters of distilled water. We observed a green color. Now, this green color is likely due to the presence of manganate ions, MnO4 minus ions, which take place when potassium permanganate reacts with a slightly alkaline solution. That could be due to exposure of water to oxygen in the air, but all that's being asked of us is to write down our observation. Now, a series of test tube reactions are also carried out with Fa5, and we know that we have manganese ions involved, but we just don't know with what oxidation state. However, these series of reactions can give us an indicator as to the metal's oxidation state and the compound as a whole. So there are no changes with these two, but there is a change when we add aqueous barium chloride or barium nitrate and we get a white precipitate. This is a very obvious indicator to the presence of SO4 minus ions. Now down here, test 3, when we add aqueous sodium hydroxide, we get a cream precipitate that's insoluble in excess. And if we turn to the very back, we can find that for manganese 2 plus ions, the reaction with sodium hydroxide gives an off-white precipitate that again is insoluble in excess. So we can use that to confirm the presence of Mn2 plus ions. Now, it also gives us additional information as to the reaction that takes place with hydrogen peroxide, and that is a black solid, most likely from manganese dioxide, effervescence due to the formation of O2, which relights the glowing splint. That is because a redox reaction occurs when manganese 2 plus ions react with hydrogen peroxide, but really we only need these two to realize that we have manganese sulfate. Our last tests are for Fa6, and there are 2 observations for test 2 and test 3. In test 2, HCl forms chlorine, which means oxidation must have taken place, and H2O2 forms oxygen, which again means oxidation has taken place. That means the Mn ion is within a compound that acts as an oxidizing agent, and the compound we know to be an oxidizing agent is manganese dioxide. So now what is being asked of us is to give the metal identity. So it's become very clear now that it's manganese, and now it's asking for oxidation states within each of the metals within each compound. So our first compound was potassium permanganate. Then we had manganese sulfate, Then we had manganese dioxide. So the oxidation state in potassium permanganate is actually +7. In manganese sulfate, it is +2, and in manganese dioxide, it is +4. So you may already know these oxidation states off by heart, but we can calculate them. So for our first compound, for example, KMnO4, the oxidation state of group 1 metals is always +1 in compounds. Oxygen is -2, but because it is 4, there's an overall of -8. It's a compound, a neutral one, no charge, so our oxidation states need to add up to 0. Therefore, we get X equals +7. If I were to arrange this in an equation, for example, so I would do 1 plus X minus 8 equals 0, and you'd get X equals +7 for your oxidation state. Now, if I were to do the same with the second compound, MnSO4, now actually I already know that SO4 as a whole has a 2- charge, so our Mn must have a 2+ charge so that they can equal 0. And for our MnO2, we know oxygen has an oxidation state of -2. There's 2 of them, so overall -4. So our manganese must be +4, so they add up to equal 0.